Good morning and happy snow day. This is an abbreviated lesson I was going to do in class, arc length and surfaces of revolution, not volume, but actually the surface area or the shell of that object that we rotated last week. This is a pretty cool lesson, arc length. To start off with, I've got the function y equals square root of x, and I have a designated interval from 0 to 4. So the first thing I did was just draw a line from basically the secant from 0, 0 to the point 4, 2. And you can see because of the way you have a curvature over the top of this line segment that we could do the Pythagorean theorem here to get the length of the line. This is 4 and this is 2, and that's why I came up with this to be square root of 20. So we can see that our arc length has to be greater than square root of 20. All right, so that's one approximation. It's not a very good one, just to say that it's greater than square root of 20. So let's go on to the next screen. In the next screen, I decided to split this up into two line segments. So from here to here, from 0 to 2. So now I have a change of x of 2. If you look up here, my change of x when I only did one segment was 4. And I used one segment. Come down here. Now I'm going to do a change of x of 2. And let me draw this in here. So this is 2 as well. And you can see that you kind of have to do a little bit of math here to get the change of y. But this first length is the square root of 4 plus 2, or square root of 6. And to be honest with you, I'm not going to bother simplifying this, but here is your 2 minus root 2 up here. And so the length of this line is the square root of 4 plus 2 minus root 2 quantity squared. And you add those two together, and that's our new approximation. It's still an under approximation because you really do see this pronounced arc here, which is going to be longer than that hypotenuse that we used to approximate it. I think maybe you can see where I'm going here. In the next example, I did 4 line segments. This time my change of x is 1. Change of x is getting smaller, and so I have this length. So there's that one, and this one, and this one, and this one. So I basically have 4 little hypotenuses that I've added up. And so what are we doing here? Looks like we're adding a bunch of stuff up. What do we do that with? We do that with an integral. We get a better approximation, obviously, as change of x goes to 0, and we put an infinite number of these line segments in. Okay, so what are we adding up? We're adding up the square root of change of x squared plus change of y squared. That's one of those line segments. What would happen if I divide by change of x and multiply by change of x? Hopefully you can see that that's going to cancel out. So I'm going to make a big square root here and have change of x squared plus change of y squared all over change of x squared times change of x. So these two are basically multiplying by 1 because the square root of change of x squared is change of x, as long as change of x is positive. You all know that the square root of x squared is really plus or minus x, but in this case, length is a positive quantity, so I can just say that the square root of change of x squared is change of x. So remember, this is just multiplying by a very fancy 1. Okay, let's clean up what's underneath this radical. So each distance is the square root of 1 plus change of y over change of x, quantity squared, change of x outside. Okay, what happens when change of x goes to 0? What is change of y over change of x as change of x goes to 0? Well, I believe that is the derivative. So here is what you're adding up. To get arc length over an interval from A to B, you're going to add up 1 plus the derivative, and usually we write it as f prime of x because these are functions, but it could be dy dx, quantity squared dx. And so this is a physical, countable number of line segments. Each one of those line segments, remember, being the hypotenuse of a right triangle, and this would be the infinite number as change of x goes to 0. So bottom line, this is your lesson right there. That's how to find arc length. You integrate from A to B the square root of 1 plus the derivative squared. I'm going to throw an example in here that I didn't have before. I'm going to use the function, it's a really bizarre function, ln of cosine of x. Okay, and it actually looks like this. The cosine of 0 is 1, and the ln of 1 is 0. So I have the point, I have the point 0, 0, not 0, 1. ln of 1 is 0. So I've got the point 0, 0. And if I do this from 0 to pi fourths, I actually have a curve that looks like this. So I'm finding the length of that curve. So the first thing we do is we take the derivative. So we need a little chain rule here. F prime of x puts cosine on bottom, and the derivative of cosine is negative sine. And then for the formula, you need to square this. So f prime of x squared, let's see, that's negative tangent, so when I square it, I get tangent squared. So to find my arc length from 0 to pi fourths, I have the square root of 1 plus, and the reason I chose this one is it came out so nice and pretty. A lot of times you're going to find on these, because you're dealing with a radical with nothing in front, that you really don't have a technique of integration other than your calculator to solve these. So a lot of them will be set up and do not solve, and you've kind of gotten used to me on that. 1 plus tangent squared. I love tangerine sections. So now I'm going from, and my pen's not working. I don't know why this does this at home when I'm videoing, but works perfectly at school. Does anybody have an answer for me for that? I would give bonus points for that. Okay, so I've got secant squared under the radical and the square root of secant squared as long as secant is positive. And between 0 and pi fourths, secant is positive. So I can just drop this to a secant x. And I am laying money that most of you don't remember this integral because I really didn't hold you to it first semester, but it's going to need to be part of your repertoire now, is the ln of secant x plus tangent x. And we're evaluating this from 0 to pi fourths. So let's see, the secant of pi fourths. The cosine of pi fourths is 1 over root 2, so the reciprocal is root 2. The tangent of pi fourths is 1 minus the ln. The secant of 0 is 1. And so this is ln of 1, which is 0. So bottom line, there's my arc length, and that's how to do that. Okay, so there's your lesson. I'm going to talk to you about surface area one day in class when I can get it in there. Seriously, arc length is way more important for you to retain. Here again is our lovely curve from 0 to 4, the square root of x. And then I noticed that this interesting from 2015, and don't be alarmed that we got to things earlier in 2015 than we do now. That was back on the old schedule, and things just moved a lot more quickly. So this was like a little, what all can we do with square root of x over this interval? You know, find where f of x increases. Well, you know what this looks like, so you could answer this question without calculus. Concavity, same thing. But how do you do it with calculus? You tell me where the first derivative is positive. Equation of line tangent, so this would be A is looking at the first derivative, B is looking at the second derivative. Hopefully everybody has retained the equation of a line tangent. Mean value theorem, MVT. That would be a great question for you to do. Average value, we looked at that the other day. Length of the curve is new. Woo! Length of the curve is new, so now I would want you to actually find the length of the curve. I believe you'll want to set up that integral and do the math in your calculator to give me a numerical answer. And same thing for f, volume around the x for that region and volume around the y. If you have time between now and Wednesday, I think it would be awesome for you to do these problems. I am not going to grade it, but I will post the answers for you. I hope you have a nice day off. It's nice and cold. If you have some work you need to catch up on, but I didn't think it would hurt for you to take a look at this video. So I will be sending it out soon. Have a great day, and I'll either see you around campus tomorrow or in class on Wednesday. Bye.